as I said, welcome everyone. I'm Claudia Mazza. I'm a professor in biomechanics at the University of Sheffield in the UK, and I'm here representing the Mobilise-D as a work package leader for, in the technical work package at WP2. What is Mobilise? Mobilise is a large consortium, a large effort set up for connecting digital mobility assessment to clinical outcomes for regulatory and clinical endorsement. It's an initiative funded by the IMI2, and we have received fundings from both the European Commission and the European Federation of Pharmaceutical Industries. It's a 5-year project, so we are set to finish at the end of March 2024, and we have 34 multidisciplinary partners that include both public institutions, pharmaceutical companies, SMEs, and other technological partners. And the consortium is very, I would say, very effectively led by Professor Lynn Rochester from the University of Newcastle and Dr. Rubinov from Novartis. But so the first thing that I wanted to discuss with you is really why we have put together such a big consortium and why are we really getting all this support from the funding bodies. Mobility, for us, of course, is physical mobility is what we are talking about, is the ability to move freely and easily without assistance. In an aging society like Europe, but of course is the same that is happening across the world, the society is becoming older, and as a result also less physical mobile. This of course has impact at personal, societal and economical levels, and the priority for our healthcare systems is to try and mitigate mobility losses and its consequences. The problem that we face though is that there is a clear need at this stage of for a consolidated approach to measure mobility. And this is really the goal of our project, to provide validated measures of mobility in different cohorts of patients, including Parkinson's disease, multiple sclerosis, proximal femoral fracture, and chronic obstructive pulmonary disease. And this is really because we believe that this can help us making an impact to inform therapeutic development, clinical practice, precision medicine, to facilitate clinical trials and drug development, to develop a roadmap for the clinical implementation of innovative tools to identify, stratify, and monitor disability, and also to, which of course we all know that is a very well-known need at COVID times. We have learned in these 2 years of pandemic that how important it is to enable cost-effective and wide access to clinical management and personalized healthcare. The issue we face when we talk about mobility is that mobility needs to be assessed, can be assessed in very different ways. It is a multifaceted problem that needs complementary tools. The first thing, the most common, is that of asking and investigating what is the mobility perception. So by asking a patient whether they feel they are mobile or not. And of course, this cannot be so reliable. So typically there is, this is accompanied by structured measures of an individual mobility capacity, where we ask our patients, for example, to perform some structured tests that entail some sort of measurements of how far or how fast they can go. And then there is another domain, which is really what we are interested in, which is what happens to our patients when they leave our lab and when they move out and about in the world. So what is it they actually do rather than what they can do. And we can measure in the lab. So the mobility performance is really the focus of Mobilise-D. And our assumption is that the mobility disability can be intended as a loss of mobility performance in association to the most important mobility-related activities of daily living. And in particular, among these, we decided to start from looking at Gait and focusing on Gait as the most essential of these ADLs. The tools that we have decided to use are IMUs. We are developing a device-agnostic approach where we basically want to prove that any IMUs that can record data from 3 accelerometers and 3 gyroscopes for 7 days continuously 100 Hertz can be used to monitor, in the real world to measure mobility performance. What we obtain from these sensors are a number of signals and that need to be processed with specific algorithms in order to extract a number of metrics of that can quantify mobility, so which are what we call our digital mobility outcomes. The way we approached this problem is not that of selecting one single outcome, but to look into all the possible outcomes that could characterize mobility in our patient cohorts and develop all the needed algorithms to calculate these DMOs. We are then using a study that we call the technical validation study in order to assess the accuracy and reliability of the algorithms that we use to calculate these DMOs, and then and to establish whether they can be used to detect minimally clinically important differences. If this is possible, then those DMOs will be included in our clinical validation study that will establish their construct validity, predictive capacity, and ability to detect change. And at the end of the day, what we will be able to select from this process is the selection of the best performing DMO for each disease, and if it's possible, the best performer across diseases. So as I said, this first seminar today is really the first of a series of seminars that we have set up to share our experience from the development of the algorithms down to the validation. And we will be presenting all the issues that we and how we have decided to deal with the characterization of the devices and make our approach device agnostic, how we're using, how we set up a protocol that would allow us to validate the DMOs in the real world for the specific populations of interest, and how we are processing and analyzing our data in a standardized manner, and all the results and some of the lessons that we are learning from the processing of this data. Before giving the stage to the first of the presentations for today, I will just stress the fact that whatever we are presenting today, and including what I just told you, is of course our own opinion, not that of the IMI or the EFPIA or the European Union. So without further ado, I'm happy to leave the stage to Felix Kluge, who was one of our young researchers in the academic partners that now has joined Novartis very recently to keep working on the project from there. So, Felix.
Good, thank you, Claudia. So, basically in supervised clinical or lab-based assessments, what we typically assume is cyclic or regular cyclic walking patterns. And this might be true for standardized tests such as the 6-minute or 10-meter walking or the timed up and go test. But if we want to quantify how patients walk in their everyday life, so what Claudia was talking about, we will encounter walking patterns that we maybe did not expect, also in conditions that we did not anticipate. And as already mentioned, there's therefore a need for technology that can assess mobility and gait across heterogeneous walking and in changing and complex situations. So going into the real world, we, however, encounter a manifold of challenges influencing the outcomes. And we need to think before starting to implement technology about some questions. For example, which outcomes do we want to assess? What do we consider walking? Do we want to include walking aids into our working definition of walking? And what is actually this real world we're talking about all the time? So what we faced in the beginning was the problem that there was no common terminology regarding real world gait assessment. And there was no consensus on that. And furthermore, there are so many heterogeneous measures across all the different disease areas that it was difficult to basically settle on just like one approach on how to measure walking in the real world. So there was a need for a common working definition on how to assess walking in real world conditions, also across disease areas. So the first step, what we did is we identified different domains which we wanted to look at with regard to real world walking, and then also specified some very concrete terms which needed a more thorough definition. For example, how do we define walking? Do we base it on the standard traditional definitions we know from literature? And what is real world? Is it only outdoor, also indoor walking? What about clinical settings, and so on and so forth? And we will dive into that a little bit later. In the next step, we tried to propose, or we proposed actually initial definitions for those terms based on literature. And in a consensus process based on a Delphi approach, which we conducted online and anonymously, we actually integrated expert knowledge. So we asked experts for their agreement on our initial definitions. And we asked that on a 5-point Likert scale. And we defined some a priori, some threshold with which we wanted to assess the agreement or the consensus. And we actually found, including the feedback of the experts, we found in 2 rounds of asking those experts a valid and a solid consensus on all definitions we actually posed. And we will come to the definitions in the next steps. All in all, we included 51 participants from which we got input in both rounds, and you can actually find more on the methodology in the paper we published just last year. So let's come to some definitions, and let's take maybe real world as the most important one, because we're talking about that all the time. So in our consensus, we found that real world relates to the context in which walking takes place. That's clear. And that is free living, unsupervised, uncontrolled, and non-standardized. And furthermore, we also assume that all walking assessment is unscripted. So there are no instructions given to the participant or the patient interacting with the device. And also there should be no interaction needed to operate the wearable device. So it should be as unobtrusive as possible. And last, real world also is distinct from any laboratory-based test, from supervised tests, supervised meaning fully controlled and observed, or any semi-controlled test, meaning walking freely, but still with supervision. For walking, we based our assumption on literature as well. So we define walking as a method of locomotion using both legs. So it's walking in an intended direction. And more specifically, we also included walking with walking aids is included because we wanted to also cover patients with more severe disorders. So we want to be able to assess walking and the respective outcomes of those patients as well. We also decided to define a stride because that will, and you will see it later in the algorithm implementation, a stride as interval between 2 successive initial contacts of the same foot. And when we look at a more coarse overview, and if we aggregate strides into so-called walking bouts, from those walking bouts, you will see later, we can actually derive mobility outcomes. And in our consensus process, we defined that a walking bout is a walking sequence containing at least 2 consecutive strides of both feet. And if you think about that and you see the example in the lower left, that means that we have at least a sequence of right, left, right, left, right, left steps, or the inverse, starting with the left foot. But walking bouts can, of course, be longer, but that's our minimal definition here. A walking bout can be terminated by any other period consisting of resting or any other activity that is longer than 3 seconds. And then it can be followed by any other walking bout again. And this definition allows us to be quite flexible regarding walking bout construction. For example, we can also allow small breaks to be part of walking bouts. For example, single misdetected steps due to algorithmic errors or something similar do not just break a walking bout into 2, but we still keep 1 walking bout, which we can analyze regarding our outcomes. In the end, for each detected walking bout, digital mobility outcomes such as walking speed, mean walking speed can be calculated. But as also mentioned previously, walking speed is not the only outcome, but mobility can also be defined as a combination of other parameters, and those can include, for example, cadence, stride duration, stride length, step duration, step length, the walking bout duration itself, or the number of strides in a walking bout, or even other secondary DMOs which we will talk about also later on today. However, there are some assumptions we need to fulfill in order to obtain reliable parameters. First of all, we need to be able to actually extract those single strides from continuous gait sequences. So we need a robust stride segmentation, which will also be part of the next presentations. And then, based on the identified strides, we need to pose further constraints, which determine whether to include a stride in the construction of a walking bout. For example, unphysiological strides, too short or just too long, need to be excluded to not skew the outcomes. And also, we need to be able to differentiate walking context and define like further criteria to distinguish level from incline walking or turning to make sense of the actually derived parameters in the end. So all in all, extracting real-world parameters, DMOs, is not only like one straightforward algorithm, but needs consideration of which single algorithms need to be included in a pipeline. And this pipeline will be part of the next talk, which will be given by Arne Küdele.
Yes, thank you very much, Felix, for the introduction. As Felix just said, we now have definitions. We know what we want to measure, but one of the core questions of WP2 is not only what we want to measure, but also how we want to measure it. So more specifically, what are the best algorithms to measure the digital mobility outcomes Felix just described? Or more specific, as you will see throughout this presentation and the coming ones, what is the best algorithm to calculate real-world walking speed, which is our primary digital mobility outcome? The approach we are taking in Mobilise is a very basic, I would say. First, we start with identifying algorithms that are existence in literature and the community. So we gathered a huge list of various algorithms. Then we started to implement these algorithms, improve them where necessary, and finally, and this is what you're not going to hear today, but in one of the future seminars, we evaluated and compared them in a very standardized way. But when starting this process, you will come across a couple of pretty big issues really early on. The first one is already introduced by Felix. There is no common definition for certain digital mobility outcomes and other intermediate outputs, meaning it's not as easy as comparing two different algorithms from literature, as they might not have the same definitions for the output. And even worse, because we now have a very specific definition that we want to use in Mobilise, most of the outputs we find in literature do not comply with this definition. Meaning, if we want to compare them and use algorithms for Mobilise, we need to modify and augment them to fulfill our definition. The second problem is that it's not a single algorithm to calculate real-world walking speed or any other DMO. It's a pipeline of algorithms. And this pipeline is also not conserved between publications or approaches, meaning one algorithm approach might go directly from the raw signal to the real-world walking speed by means of some machine learning algorithm, where some other approach would take a multi-step approach. First identify strides, then identify cadence, and then finally identify the real-world walking speed. Meaning the first issue we faced was to come up with a pipeline that can be used to map all the algorithms that we found in literature, so that we then can test and find out what the best algorithm for each individual step in this pipeline is. The pipeline we came up with looks like this. We start with a gait sequence detection, which basically identifies gait and walking within a continuous sensor signal. This is extremely important for real-world gait analysis, because there's a lot happening in our day-to-day life which is not walking. Then these extracted regions are pre-processed, which means a sensor alignment and additional filtering that has been shown to be beneficial for further steps. Within the signals, we then identify initial contacts or steps. And for some algorithms, we just take these steps and calculate cadence. But this is one place where we needed to accommodate different pipeline structures found in literature. We can also calculate the cadence due to other measures, for example, frequency-based approaches instead of just taking the steps we found. In parallel, we can calculate step lengths, again, with a variety of methods you will learn about later on. With the step lengths and cadence in place, we can directly calculate real-world walking speed. So this is not a real algorithm at the end, but just a simple equation to get there when we already have step lengths and cadence. This pipeline structure solves the second problem I outlined. With that, we can test out individual algorithms for each of these blocks. And by combining the best algorithms we find for each block, can build a pipeline that is ideal to measure real-world walking speed or any other DMO we want to test against. However, does the real-world walking speed of this pipeline comply with our definition? No, not really. There's nothing we put in there that makes sure that our definitions are met. And actually, we create a kind of a hen and the egg problem. If you think back at what Felix said, our DMOs are based on walking bouts. Our walking bouts are defined based on strides. And what we consider a proper stride is based on the gait parameters for the stride. Meaning at the very beginning, we have no idea if a certain sensor signal should be part or should be considered a proper walking bout. The only way we can do that is as a post-processing step, meaning once we know all the parameters, so once we have parameterized the gait for our entire signal, we can then go and find out the regions of gait that together make up one walking bout and calculate the DMOs within. This post-processing step is called the walking bout assembly in our pipeline. It's basically a new structure we thought of and conceptualized in the context of Mobilise-D. And with that, we basically group identified strides together to what we consider walking bouts. And then within the walking bouts, average or take the standard deviation of calculated measures like the walking speed, the step length, or the cadence to get actual mobility outcomes for each walking bout. But as Felix mentioned, we need to identify context. So straight walking is obviously different than curvilinear walking or incline, decline walking or stair climbing, which might all be detected by algorithms that we implemented as Gait. This means we need additional algorithms here summarized as walking context that can identify things like the change in inclination during walking or turns in a continuous signal. So there were a set of algorithms that we needed to implement to make sure that the walking bout assembly has all the required information to separate out like signals or regions of straight walking from different types of walking context. But there's still one issue right in the middle of our pipeline. And that is, I was talking about step detection and step length all the time. But if you might remember, Felix said we based everything on strides. And just to recap, our step is the time or the duration from one initial contact to the next, but our stride is the duration from one initial contact of the same foot to the next initial contact of that foot, meaning one stride is basically 2 steps. But if we are working with a sensor on the lower back, many algorithms are designed to detect steps because it's easier in a sense, and we will see that in a second. And even more algorithms don't consider steps as their granularity at all, but rather they just provide an output for a certain time window. For example, a machine learning-based algorithm that takes, let's say, a 3-second window as input and then provides a value of cadence for that 3-second window. If we want to provide our DMOs based on stride-based definitions, we need to make sure that we at least provide an approximate value of each of the calculated values per stride. And the way we do that is by introducing a separate stride detection algorithm or mechanism via an algorithm that can identify the left and the right initial contact, meaning which foot made each initial contact that we detected. From that, as I just said, we can identify strides and then use an interpolation approach to get an approximate value of each of the calculated parameters per stride, independent of if the original algorithm provided a per step value, a per second value, or a per stride value directly. With that, the walking bout assembly has all the information that it needs to comply with the definitions we provided. So you can already see that a lot of work that we did in Mobilise is hidden in these screen blocks. So things that were not considered in many publications in the past, meaning there were a lot of algorithms, and you will hear some numbers today and also in the upcoming seminars for the main blue blocks. But a lot of the complexity that we now have in this pipeline is hidden in the green blocks. And this is, of course, that's why we are proud to share this work with you. But Claudia also mentioned we want to go beyond real-world walking speed, right? There are a lot of different indications. We want to measure a bunch of different DMOs. The pipeline I showed you is sufficient to calculate real-world walking speed and provides us a way to find walking bouts, so our primary time granularity we want to work on. But for the final pipeline, we kind of sneaked in a little plug here at the end, which you will hear about later, which is not really small at all, because once we have the borders of our walking bouts, we can, of course, take that signal and calculate whatever we want based on that signal. And this is basically where all our secondary digital mobility outcomes come in, like gait asymmetry that we can calculate from the signal, or other measures that we will hear about later. With that, we wrap up the first part of the seminar, and we will have a short Q&A session about what you heard so far. Thank you very much.
So I apologize, I forgot to mention at the beginning, I hope you've read it in the chat. So we would like to receive questions from you in the chat as we speak. We're more than happy to, and we might try to assess them in real time, answering the text or just reading them out loud and discussing them. So I hope you got the gist from these initial talks of how complex it is when you start digging into mobility and all the aspects that affect mobility. So both in terms of the assessment, but also when it gets, so the real work that we did here was to really try and come to a formalized version of all the issues that would allow us to implement the right things. So even just simply starting from how many strides we need to include in about down to how we implement this in an algorithmic form. And I'm sure that many of the people online today might have experienced this in their own applications. And it's really the place where we felt that the literature was most patchy, as Arne said before. So I don't know if there are questions specific to Faye. How accurate is the detection of which foot is stepping from waistbone? I don't know. I could say you need to wait for the last seminar, but I think that we're going to go now into the details of what we are seeing in the different blocks. So I'm sure that Martin will give you more information about this. It's one of the things where we are that is tricky, and again, it's one of those things that we sort of thought that there would be more literature on, but whereas we ended up having to develop and validate new algorithms for that. Ashar, the question about device agnosticity, we are trying to develop again, this is something that we will discuss specifically in the next seminar in 2 weeks. What we are doing is developing an approach where we establish the minimum requirements that a device needs to have in terms of the quality of the signals that they provide. So as I said, it needs to have a certain sampling frequency and a certain duration of the battery, measure certain signals. So we have developed a methodology to test the accuracy of those devices from a metrological performance. And the assumption is that every device that is equivalent to what we are using here would be suitable to be used and in combination with our algorithms. That's why today we are only talking about the algorithms, whereas next seminar we will be dealing more with those questions. Arne, there is one for you. For a rest period to separate two walking bouts, how long should it be at least?
I guess it's to Felix and me, but I can answer and Felix can
yeah.
add to it if you're missing something. So at the moment, we are working with an operational definition that was based on the consensus and also experience from the people in consortium of 3 seconds. But something I didn't go into detail. So the way we conceptualized this idea of a walking bout assembly was that it should be possible in the future, in case it turns out that some of these restrictions for a walking bout may lead to digital mobility outcomes that are not sufficient to recognize the clinical measures we want to actually measure, to change such values in the future. So at the moment we are running with 3 seconds. If it turns out that this is not the best approach, and it looks like it is a good approach based on our initial tests, all the tests and the work we did so far, but if it turns out it's not, then this is something that we might be able to change.
just to add on this, Felix showed the paper that we have published, where we have shared the definitions that we have conceptualized, and also this type of details are in there as well. So we are trying, as a consortium, the spirit that we're working with is trying to share all the different steps of the process and all the different methodological choices as soon as possible and as soon as we have them. So Felix's paper was actually the first one that came out in this direction. Felix, thanks. Is just send the link in the chat so that people can access that and see what we're working with.
Yeah.
So I don't see Lorenzo, a very good question. Whether we what is the robustness with respect to the IME locations? We have as a consortium, we were set with one question, which is what happens if you put with a sensor that is located at on the pelvis. And of course, there are different way of touching a sensor that will influence our results. At the moment, so our main device is attached to the pelvis with a belt, but we are also doing some testing, and we tested the equivalency of another solution that is another device that we attach to the pelvis with a double tape, with some fixing directly to the skin. Of course, each algorithm has its own sensitivity with respect to the device's location, but that goes well beyond what we can do even in Mobilise. So we are doing some work around that, but our assumption is that the sensor is located on the pelvis, on the lower back, I would say more than there is a question from Alan saying that the definition of a walking bout seems very close to what would be excluded as gait initiation. Should a minimum bout length have a sufficient number of strides that it can be considered steady state and can produce reliable gait features via ISCCS? Oh, sorry, Alan, because I think you only sent it to me. We started with a minimum assumption, which is that of 2 strides. But we are indeed we will be looking into the effects of what will affect the accuracy of our algorithms in terms of number of bouts, which is, I don't know, Felix, if you want to add something to the gait initiation.
No, we didn't include any considerations regarding initiation or termination in the definition itself. It was just now facilitating actually the walking bout assembly. And regarding the accuracy, I mean, that's like one step further in the future, looking at how accurate are short walking bouts versus longer walking bouts and so on. Yeah,
I can anticipate that what we are observing in our real world data is that you need way more than a few strides to get reliable real walking speed estimates, no matter what algorithms you're using. But again, let's wait for the last seminar and we will review.
There's also an interesting aspect, if I might add, that we're now observing when looking at the algorithm results, and that is, of course, we have the algorithms we have developed. Some of them are better at detecting and parameterizing gait during initiation, and others might kind of, not by design, but because they don't work well during gait initiation and termination, might not even detect the first step of such a sequence, meaning that the actual walking bout that we get from our sensor system might not include the termination initiation strides because a certain algorithm cannot detect it. But this is, of course, something that we're also evaluating and looking at. But it's important to keep in mind that at some point there's this interplay between the definitions that are a little bit based on this idealistic approach that we can detect and measure everything, and the actual reality that the algorithms introduce errors or might not be able to detect certain regions of gait perfectly.
Yeah, so I will keep the next 2 questions for the so the next question for after the talks where we present the algorithms, because you will notice how varied the series of algorithms we are using is. So in terms of whether they could run on near real time or not, that was the question. We are not what we are presenting today will not answer your question, Mahmoud, about how we are presenting data to the users, because that's the approach we are using here does not provide immediate feedback to the user. At the moment, we are just developing the algorithms to get accurate measurements of DMOs, but we are not doing any intervention, so we are not feeding back the information about mobility directly to the patient. It's outside our scope at the moment. Okay, so Annie, I think we can start with, so we will now go into more details about the specific algorithms that we are using for the blocks that you have been seeing. So again, there might be some more answers to the questions that have been asked. Please, Annie.
Okay, so the pre-processing. This block includes algorithms to correct the sensor orientation and to enhance the meaningful features in acceleration signals. The robust estimation of gait parameters, speed, for instance, necessitates representation of body movement in a standard referential system. And this is particularly important for real-life recordings, where the orientation of sensor can change during monitoring from day to day or even during one day. So the pre-processing stage includes a complementary filter that combines information from accelerometer, but also from the gyroscope to correct the orientation of the vertical acceleration, and then a principal component analysis, or a PCA, during each walking bout in order to align the anterior-posterior acceleration with direction of movement. The pre-processing includes also filtering and enhancement of step-related features. Steps are usually detected from the acceleration signal as prominent peaks. However, in the case of slow, impaired walking or usage of walking aids, this information is hidden in movement artifacts. And this plot here shows a walking bout recorded in a patient with slow or impaired walking. And it can be seen that it is very difficult to identify a consistent pattern of prominent peaks and to associate them to the actual steps as, for example, were detected by a reference system with sensor or lower limbs. So the processing of this type of data was challenging. In the technical validation study, we have cohorts of patients, MS or hip fracture. So the performances of state-of-the-art algorithms were not very satisfactory. We can see here that we can see three approaches, the most relevant from the first screening of state-of-the-art. And for example, this is one of the methods, so it is very difficult to identify here a consistent pattern. It was also at the beginning very disappointing because each of these methods use different approaches. So for example, filtering or wavelets, or even sophisticated approaches as, for example, morphological filters. So it was a need to put an effort to optimize these methods. And these are the results. So finally, we just try to combine, for example, the different approaches. And it seems that with this, there is a specific filter which includes the threading and low pass filtering combined with continuous wavelet transform and a Sabitzky-Golay filter. It is a kind of generic filter that was combined with the different methods from state-of-the-art. And in this way, we have satisfactory results. And this enhancement of step-related features are very useful for the next steps in the pipeline. For instance, step detection. So I will introduce the next block, which is related to step detection using information from step-related feature enhancement.
Okay, so I will continue first of all with the block of gait sequence detection, which we saw earlier is the very first block in our analysis pipeline. So it's essentially receiving the whole recording we do with our IMU. And yeah, we heard earlier already that a reliable detection of gait and also, of course, the rejection of non-gait from the sensor signals is very crucial for an efficient and accurate gait analysis. And yeah, a correct gait sequence detection allows that only periods of signal that contain gait are forwarded to all the subsequent blocks in the analysis pipeline. And this ensures efficiency and also high accuracy because all the remaining blocks can rely on that fact that they are actually only dealing with gait data. So considering that, for example, PD patients often only spend less than 10% of a day walking, we need efficient algorithms to first identify these sequences of gait in the raw signals before applying more complex steps in the processing pipeline. So if we look at this plot where we see a whole day recording, we see that there is a lot of times just no signal because the person might sit down quiet, or just some spurious signals where somebody might just move the upper body but not be actually walking. So let's now take a look at two different approaches for gait sequence detection that we use in Mobilise-D. So the first algorithm that I want to show to you was presented by Ilus and colleagues, and it is using a frequency-based approach. So we use as input the vertical and the anterior-posterior acceleration signals. And first of all, they are bandpass filtered to the frequency band of 0.5 to 3 Hertz, which are the relevant gait frequencies. And this results in the signal that is shown in the blue plot on the lower left side. And afterwards, we cut this signal into 5-second windows. And we use additionally a 2 Hertz sine wave, shown here in green, as a template, and this represents basically a single gait cycle. And then we perform a convolution between our blue input signal and this green template signal, resulting in the red signal on the lower right side. And if we now find peaks as shown in blue in this plot, and there is a reasonable number of 2 to 15 peaks in this window, we count such a window as a gait sequence. So this was the first one of the approaches, the first one, and the next one I want to show to you was actually developed by Ani, who we just heard, and her colleagues, and it's using quite a different approach. So this one relies on the accelerometer norm, and as this basically sums up all the accelerometer axes in the 3 dimensions, it is orientation independent. And first of all, the filtering and peak enhancement approaches that we just heard of were applied here. And then we perform a peak detection, resulting in these red crosses that you see in the plot. And if we then combine subsequent steps using certain thresholds, we can summarize them to gait sequences, which are indicated in yellow here. And now, as we have this coarse detection of gait sequences, we can continue to the more complex steps. And the first one in the pipeline is the step detection. And in order to calculate gait parameters such as cadence or later on the real world walking speed, we need to first of all identify and demark the single steps. And specifically in this block, we want to find the initial contacts of these single steps. And the most common approaches for this algorithmic step are peak detection, flat phase detection, or zero crossings. And again, I want to show you 2 exemplary algorithms for this task. The first one was presented by Shin and Park, and this is using a zero crossing technique, and it's also based on the accelerometer norm. So in order to reduce noise, a sliding window summing technique is first applied to this accelerometer norm. So this is basically a low pass filter. And afterwards, a differential technique is applied to eliminate the effect of gravity. So it's basically a high pass filter. And finally, the zero crossings in the positive slope are detected, and they determine the initial contact time points. So this was the first algorithm. The second for step detection was presented by McCambly and colleagues, and they used the vertical acceleration, which is smooth by first integrating it and then differentiating the signal using a Gaussian continuous wavelet transform. And finally, the minima in the signal shown also in the plot here, they represent the initial contacts. And in Mobilise-D, we use this algorithm with additional improvements using these pre-processing techniques that we saw in the beginning. And with that, I would like to pass the word back to Annie, who will continue with the cadence estimation block. Sorry, Annie, you need to unmute yourself first.
Okay, thank you. So the cadence of detected walking bouts can be estimated, and it was implemented in the pipeline using two approaches. So we have the time domain approach, and in this case, the cadence is estimated as average of step frequency, and it is essentially based on the detection of temporal events from the previous step detection algorithm. And we have also implemented a frequency domain algorithm. Frequency domain estimation of cadence is usually based on the detection of the dominant peak in the spectrum of acceleration signal. But again, so this spectrum can be very noisy, and it could be when we have the case of impaired walking, difficulties to process and to identify this dominant peak in the frequency domain. So to improve the estimation, we apply a comb filter, and this type of filter allows us to enhance the frequency-related spectral components. And then we use a maximum likelihood technique to estimate the cadence. So it is an estimation of the cadence. In the first method, the spectrum is obtained from the norm of the acceleration signal. But based on our experience, the norm is a nonlinear operation. So it is possible that it might distort the signal. So there is another technique that we have implemented and tested. The idea is to obtain the overall spectrum from the individual spectrum. So we first apply FFT to each individual axis, and then we have the overall spectrum as the sum. And then we apply the same approach using the comb filter and the maximum likelihood technique to estimate the cadence. So we have two approaches. Based on our experience, the frequency domain approach can be more accurate if we have long sequences of walking bouts, even if the signal is noisy. But the main issue with the frequency domain is that, especially in mobilized population, the walking bouts are short. So it is very difficult to say which method, which approach is the most relevant. So each of them has advantages and limitations. There is a possibility we have tested. For example, if we have several algorithms, try to combine the best of each one. So kind of combination of, example, to have the output of several algorithms, and then to have an average of the estimation based on the output of each algorithm. So these are the main techniques. We have algorithms we have implemented related to the Cadence. Now, the next step in the pipeline is step length estimation. In fact, this is one of the most challenging block in the pipeline because there are three main approaches to estimate the step. So we have the model-based techniques, we have the direct integration and machine learning techniques, but the main technical issues, for example, for the biomechanical or empirical models, is that we need to adjust some correction factors. For direct integration, it is well known we have this problem how to remove the integration drift. And for machine learning models, the main issue is how to cross-validate the models, how to get data, and to have an appropriate approach to train and to test the models. Related to the first class of algorithms, so those which are called model-based, in fact, there are two types of models, those which are based on biomechanics. There are two main biomechanical models we have implemented, and they are well known in literature. You can see some references here. And there are also the so-called empirical models. In these models, so they are based directly from the raw data. This is why they are called empirical. And these kind of models were developed mainly in the field of M-health. So with so how to estimate, for example, step lengths with devices which are not fixed on the body. So this is why in this case, it is not possible to use biomechanical models. For both, so the main limitation is that we need to fine-tune some correction factors. As we can see, these are the equation, for example, for the biomechanical models. We need to correct these factors, and we need also in the model to include information from subject, so anthropometric data. Of course, we have this issue, which are the most appropriate techniques to remove the drift after the integration of acceleration. The classical approach is to use high-pass filtering. There is also more sophisticated methods, as for example, empirical mode decomposition, which is relatively intensive processing technique. But the advantage is that with this technique, it is possible to have a kind of data-driven estimation of drift. And related to the algorithms that use based on direct integration, we in the framework of work package 2, we develop an algorithm. It is a very complex, in fact, it is a combination between model-based algorithms and some techniques to address this issue, which is the correction, removal of integration drift. And this more details can be found in a recent publication. And regarding the third type of methods, so the classical machine learning, our approach and our contribution in the framework of Mobilise was to try to define what we call heuristic or interpretable features. That means that if we have, for example, from the other algorithms, a kind of estimation of step lengths or some biomechanical features, we can integrate then into models. So try to don't use as features kind of a black box, just statistical features extracted from the raw data. So another contribution was to understand how to train the models to avoid overfitting. So so we take this opportunity. We are a big consortium. It was possible to use some existing data from consortium, for example, to train and to develop the models. And then these models can be used for the technical validation. And in this way, we can avoid overfitting. And also we try to evaluate different models, for example, to see how the estimation, the error change if the models are trained by specific clinical population, or if we combine data from different populations. So these are the main techniques we try to apply or to investigate, to evaluate in order to improve the algorithms using machine learning. So next.
Okay, so I will continue with one of those green blocks that were presented to you earlier as the kind of special extra things we need to do real world gait analysis. So we heard earlier that, of course, we are in this case dealing with sensors that are attached to the center of mass. And therefore, if we detect steps, we detect them within one sensor from both the left and the right feet. But Arne explained to you that our definition of walking bouts is based on strides. So we need to know, in fact, which of those steps come from the left and the right foot to determine strides on one hand. And also later on, if we want to derive some asymmetry measures, we need also to know which of the DMOs come from the left and from the right foot. And therefore, we needed to think about how to determine this laterality. So as we heard earlier, this was one of the algorithmic tasks that hasn't been covered so much in literature so far. Therefore, myself and the colleagues in the project, we developed a new left-right detection based on machine learning, which was presented recently at the EMBC conference. And it uses the gyroscope from the anterior posterior and the vertical direction. And this is basically capturing the rotation of the hip during walking. So in the beginning, we apply some pre-processing to smooth the signal. And then we look at some signal characteristics or features at the time points of the initial contacts. So you see in the plot, the vertical gray lines represent the initial contact time points, and the orange line is the pre-processed gyroscope signal. And then we go ahead and calculate for every of these initial contacts 3 features, which is the signal value itself, and the first derivative, so the gradient, and the curvature given as by the second derivative. And so it's illustrated here subsequently, but of course, in fact, we do every feature for every single time point, and we do it for not only the anterior posterior signal, but also for the vertical one. So this results in 6 features for each initial contact, so being a 6-dimensional feature vector. And we then pass these feature vectors into a pre-trained support vector machine, which was used from data that was available in this consortium. And this support vector machine is then able to predict if the initial contact and the feature vector we pass in was belonging to a left or a right initial contact. So this gives us a quite reliable solution for this challenging task. And because the question came earlier, so in the paper, we could show that this approach is, depending on the cohort we're looking at, able to predict the left and right initial contacts with an accuracy of up to 100%. And without spoiling too much, we could show that in the real world data, we could achieve an accuracy of close to 90%. So it seems to be quite a promising approach. And the other remaining block that we have is the walking context, and specifically we want to talk about the turning detection here, because the inclusion of turning into the analysis of real-world walking is of course essential, because the difficulty with turning contributes to the mobility, disability, and also faults in people with movement disorders. And on the other hand, also, it might happen that people are walking, performing a sharp turn, and then continue walking. And such a sharp turn will also determine a termination of walking bout and initiate a new one. So the algorithm we are looking at in the project was presented by El Gohari and colleagues, and it is based on the vertical axis gyroscope signal, which captures the rotation around the vertical axis of the body, of course. And also here, the signal is first smoothed using a low pass filter, and then extrema in the signal above a threshold of 15 degrees per second are detected, which might represent turns. And this is further fine-tuned with the subsequent steps. So we find corresponding 5 degree per second crossings before and after these extrema, and they determine the start and the end points of turnings. And after some additional checks, we return the turning sequences as shown in the lower left plot. And we can also then use the gyroscope signal to calculate the turning angle. And we see that in the example signal here, there were performed a lot of 180-degree turns. So obviously the signal comes from a gait test where a participant was walking back and forth on a walkway. So this concludes the part of the turning detection. And I would now pass on to Eran, who will continue with the secondary digital mobility outcomes.
Hello everyone, my name is Eran. I'm going to present today the secondary digital mobility outcomes. They're going to be referred to as secondary DMOs. Just a quick walkthrough on the talk. I'm going to just describe a little bit about what secondary DMOs are, which one we decided eventually to implement, and the problem with the big ambiguities that we see in the literature regarding those outcomes, and just a small couple of examples about secondary DMOs outcomes. So just reminding you what Claudia said at the beginning of the workshop, we're trying to develop in Mobilise-D a measurement tool to assess mobility. And we have 5 very different cohorts, which are very challenging. Each one has their own different mobility problems like balance, slow gait, asymmetry, sometimes combination of them. Disease severity can impact that as well. And we're trying to eventually achieve real-world digital mobility assessment and try to predict clinical outcomes, classification of patients according to the disabilities. And if just to sum up of what we saw so far, the primary DMOs were the real-world walking speed and step length and cadence. They all come out eventually from the pipeline as the walking bout DMOs. And what we're trying to add in order to help gait speed and the primary DMOs in achieving these goals are the secondary DMO. They come out right after the walking bout assembly, which Arne presented nicely today. And it actually takes all the walking bout that we consider to be according to the definition of what the walking bout is, and try to apply digital mobility outcomes to eventually help us with the goals. But which one should we actually implement? And that's a big question. At our center, we specialize with 2 of the cohorts, people with Parkinson's disease and with the MS, but we didn't have a lot of knowledge for the rest of the cohorts. And what we decided eventually to do is take the experience and wisdom of the clinical partners of the entire consortium. And we decided to send a survey to each one of the clinical partners, asking them about what are the best outcomes they actually believe can help us with achieving the goals, and provide us the outcome, which category roughly it tries to quantify in the gait, like pace, rhythm, symmetry, and durability, where the sensor is, what they use, like for example, acceleration for that measure or gyroscope. We didn't just ask for measures from the lower back. We just said from any sensor, Later on, we'll try to see if measures that are like taken from the low feet, for example, could be implemented as well from the lower back. References, of course, are a great help in order to implement the algorithms. And most importantly, if the code is available by the partners and in which language it was implemented. Most of the codes that were provided to us were in MATLAB and some in Python. In total, we created a big list of 126 outcomes. This is just a very small part of the measures that we have. And just an example of the domains they cover. For example, they cover the variability in the gait, the symmetry, magnitude, complexity, information about the turns, dynamic posture control. And one of the things that we noticed while we were compiling the list, that there's a big ambiguity in what exactly each one means. For example, jerk is a measure of smoothness, but when we went to literature, we saw that there are like 5 or 6 different methods to calculate jerk. If you look at the gait asymmetry, there are quite a lot of asymmetry or symmetry measures, and it wasn't really clear about what each one is supposed to be. And if you go to the literature and try to compare articles, it's quite hard to do. So what we decided to do is, in the code that we actually implemented, we also added a very clear definition of what we're actually calculating. For example, this is a harmonic ratio, and in the header itself, it's really well explained. It's a measure of gait smoothness. This is the theory behind what this measure is supposed to be, and what do you expect to get from this measure. For example, from the vertical nape acceleration axis, a larger value represents a smoother gait pattern. And we expect to get numbers greater than 1. And for the ML, we explain here why we expect to get numbers smaller than 1. And of course, we add in the function itself descriptions about inputs and outputs, making it as clear as possible to read in the units. And at the end, of course, we added the reference to which measure we actually implemented. And in the code itself, we also made it as clear as possible to avoid ambiguity. We explained exactly each code, which part of the article it's actually trying to implement. If there's thresholds, for example, why they are here, what it's supposed to do. This is a very small example from technical validation study. You heard that phrase several times in the workshop. So if you really want to join us, you're welcome on session 3 for the technical validation study. It's going to talk about the cohorts, the assessment, the data that was gathered in the study, patient's perspective, and I won't get into too many details, but this is just a very small example of a test which is called surface test. Subject were walking, they're standing here and walking for 4 meters, doing a turn, walking for another 4 meters over a carpet and another turn, and do that again. So you have quite a nice example of walking in a straight line and walking and doing turns. And this is just a small example of how we implemented, or the implementation looks like of the, in this case, step duration variability. And what you see here, that for healthy adults, we get a much smaller step variability as expected, and that's very nice. And in the groups with disability in their mobility, you can actually see much bigger variability. And in each group, we had a wide range of disease severity, and it's been expressed here in the variability as well. This is another example of a turn, which is the turns in these parts. This is the maximum turn velocity, and again, as expected, we see that the adults turn faster than the other cohorts, which makes sense. It's really nice to see that the implementation of the theory that we have actually is being translated to something that we actually see in these graphs. So thank you for listening, and we're going to Q&A.
So we're going back to some Q&A now. There are some questions coming outside about the algorithms and data, how and when we will be sharing them. So the idea is, as I said, we are trying to share as much as we can as soon as we have the possibility. So you've seen how I've kept sending the links of papers that have already been published. Some of them include also some implementation, for example, of some experimental techniques and data processing that we needed to use for and relevant GUI. The final algorithms will be made publicly available, and also the data that we are collecting and the DMOs that we are extracting. But of course, we don't want to make anything available until when we don't have what we consider good enough to be shared. We don't want to send out yet another algorithm that then is not clear and we cannot use. So the example that Aaron gave on how we're working on implementing the code in a transparent and rigorous manner is just one of the things that we're trying to do all the way through, so that then when the time comes to share the algorithms and the data, we will be ready. So it's definitely our intention to share whatever we can as soon as we can. But of course, we need the time to do all the work needed for that. There is a question from Arash. Oh yeah, that was about the data set. Oh, Mahmoud, well, one of our heroes, I would say, that we mentioned in so many of our meetings, as you've seen, the algorithm we are using. So, Martin, I think you want to answer to this one about the partial turns when working, and how.
I think this rather refers to maybe the walking bout assembly, because what we output of the turning detection is basically as many turns as we can get, but the question is, I think, rather how we use them in the end, or how they might be influencing our walking bouts. So we also define the threshold there, yeah. But I think Arne can comment on that.
Yeah, I can. So in general, we differentiate between, so we have the initial threshold, which is part of the algorithm, basically differentiating straight walking from anything that we consider walking, and then within the detected turns, we then again differentiate between what we at the moment consider harsh turns. So basically fast turns that are very likely to include a completely different biomechanics. And what we're doing at the moment is to identify these regions in the gait sequences, to then consider them differently from the rest of the walking. However, this, as I mentioned, this is only done for these sharp turns. So if we have curvilinear walking, so smooth turning to a certain degree, then we include that, but we basically flag the walking bouts or the region of gait around them to be curvilinear walking, so that they can be considered differently in a statistical analysis. As you might realize, I didn't provide like a exact threshold. If you're interested in that, the harsh turn at the moment, that is defined by the peak, the maximum rate of turning, and is roughly set to a value that we assume that we are close to a 180-degree turn within, I think, 2 seconds, if I'm not mistaken. But this is also one of these values that we are planning to redefine once we have a look at the results and when we can get the feedback loop in to redefine those thresholds.
Just to add on this, the reason why we wanted the sensors with the gyroscope is exactly to be able to look also at this type of information. So too many times, in the real world, we do have continuous turning. We do have like periods when the walk is not straight, and being able to classify and identify those walking bouts where there is some curvilinear walking and compare the results and the accuracy of the algorithms in both curvilinear and straight walking is definitely something that we are looking carefully at, especially because, again, spoiler alert, the biomechanical models seem to be the best performing in our cohorts. So the one based on very basic mechanical assumption of the inverted pendulum. But of course, when there is turning, that's when they struggle. So that's the reason why we wanted to have a gyroscope on board and not just the accelerometers, basically. There is a question from Lorenza. Annie, I think you're best placed to answer.
From Lorenza or from, so maybe I can, it is my interpretation for, there's a question related to bimodality.
Yeah, that's after. I was going to.
Okay, so maybe I can so it is just my opinion. I think we can see bimodality when the granularity of gait is step or stride, because we so bimodality means that we have two modes, so we have two types of behavior for a given parameter, for instance speed, and if the granularity is the working bout, so we have the average speed per bout, I think this bimodality vanish, or it is somehow smooth. So based also on my experience, bimodality can be assessed, and it is statistically significant because bimodality should be quantified with, there are some statistical metrics to quantify bimodality when the granularity or the samples are the parameters per step or per stride. So it is not so evident for working bout.
If I can add to that, so basically in the technical validation study, which is the part that we're discussing now, we are really just looking at validating algorithms at single bout level. When we will be starting looking into the clinical use and meaning of these metrics, of course, it's when we will have to move from a single bout to what can be an observation of hours, days, or weeks, and then in that case there might be these distributions to be accounted for. But that will be, for us, is the part of the analysis that goes after comes after the having established how accurate our algorithms are. And for example, what is the minimum length of a bout that we should include in such clinical analysis, and so on and so forth. So it's a complex problem, but it's our second problem to be solved, I would say. So, no, Lorenz, I think I answered to your question already by saying that we are indeed comparing this curvilinear to the rectilinear walking. There is a question about if the walking bout is defined after the step detection, how do we define the walking bout for this part to run the PCA? Arne, I don't know if you've read this. If you have anything to... So
PCA is part of correction of sensor orientation. So in fact, we have this block of correction of sensor on the top of each algorithm. And for the algorithm for working bout detection, this algorithm is based, for example, the algorithm Martin showed, or it used the acceleration norm. So this algorithm using acceleration norm don't necessitate correction of the sensor orientation because it is not necessary. I don't know if with this.
Okay.
I think to add to that, I think that the question is also in the direction, if we have like the person is like relatively fast and pretty consistently walking in a circle or just doing a lot of turning, then the detection of forward direction using principal component analysis might not work perfectly, right? Because we try to figure out like around which direct axis of the sensor we have the majority of rotation, and when the person is walking in circles, then it might be that we detect like the not really the forward direction, but the wrong axis as our forward direction of movement. Yes, this can happen. It's of course a limitation of such an algorithm, but again, it comes down to validation in the sense that we need to figure out like how often situations like these happen in the real world, and of course directly walking in a circle and turning on the spot might happen in the real world, but the question is then how much harm for our overall digital mobility outcomes do we like how bad is it if we don't measure it, if we cannot record it correctly? Does this affect how good our algorithms can be like in their specific application? And for that, I would assume like if we don't correctly identify or quantify perfect circle walking, it won't have a big influence in how we quantify the mobility of the specific patient we are measuring.
If I can add to that also, the way we have designed our validation process is that we have some, of course, some controlled in-lab observations as well, and we have tried to include a number of tasks where we have different degrees of turning and different type of path, including turning, which we are really using to test this type of very specific questions that might come up. So that's what we are using to try and learn better what then can happen when we move and apply this data to the real world. Arash has a question, Annie, for you. Is about.
Yeah, I think this type of algorithms are those related to direct integration, Arash. So in the library, so we just show a few examples. So in fact, for each block in the pipeline, we have many algorithms which are in the evaluation process. We have two, if I remember, maybe I can send you the reference of Abul Fazal paper. We have two algorithms that use this approach, so to estimate based on estimation of velocity, but I don't think they were sufficiently high in the ranking process.
So basically, what we have done is that we have implemented all these possible sorts of algorithms, and we have used pre-existing data that were made available within the consortium, where we had both wearable sensors and some gold standard data to do a pre-screening of the algorithms and then bring only a selection to the final validation, the technical validation study. So as Annie said, this paper from Abul Fazil that I have just put in the chat is where we presented the entire list of algorithms that we have tested for those blocks.
Yeah, so it was a very preliminary screening.
Yeah.
So it was based on existing data.
It was a very comprehensive type of analysis that we did. We didn't want to discard any solution without having tried it on some data first. And again, that was the positive side of having such a large consortium, is that we had a lot of data and a lot of algorithms to start with already. So we didn't have to completely reinvent the wheel. We just really tried to look into whatever was available in the literature, implement it and check it on the data we had. And again, there is a paper, we published also a paper that I'll look for the link now, where we described how we can objectively compare different, choose from different devices or choose from different algorithms, and we are still developing that line of thoughts. So I'll share that paper as well now. Other questions? So there have been many people asking about whether we will make these slides and seminar available. We do have the plan, as you've seen when you entered the room, the meeting is being recorded. So we will just make sure to have a clean, ready to go video, and we will put it on our YouTube channels as soon as possible. I would just, I don't see more questions coming. Please, if anything that you heard today was interesting or you want to know more, just get in contact with us. We're always happy to discuss and share more. We are all looking forward to more conferences and opportunities to meet in person. So over summer, you might find us around telling about all this work as well. And I would just like to share for a moment the information about the forthcoming seminars. So this will be, the next one will be around how we design the multi-centric trials and how we are testing all of our devices, both the single sensor device, but also our gold standards, to make sure that we can validate things properly and that we know which devices work well. Then we will guide you through all the journey and the assessment during the technical validation study, and how we decided to tackle the data analysis, which is also a very complex process that entails choosing the best algorithms and then assessing how well they work for each of the DMOs that you have seen. And then we will conclude by sharing the lessons that we've learned from our technical validation study and some of the preliminary results. So hopefully we will see many of you also in the coming seminars. And as I said, please do get in touch with us, and we're more than happy to share more information and more of our knowledge. So I would really like to conclude by thanking all the speakers today. I've been really lucky to work with this fantastic team, and this is just one-tenth of the team probably, so you would see more faces and more voices in the coming seminars, and I think you can appreciate this. It's been really a teamwork. So thanks again to everyone for coming today, and thanks to the guys for that presentation, and see you in 2 weeks.